Professor Dave here. Let's talk subspaces.
He knows a lot about all kinds of stuff. Professor Dave explains.
Once we understand what makes up a vector space, it is fairly easy to understand the concept of subspaces as well. To put it simply, a subspace is a smaller set within a vector space that is itself a vector space. Let's look at some examples to clarify. Let's say that V is a vector space. Now we can highlight this smaller section of V and call it S. Every element of S was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely contained in the larger vector space V, we will then call it a subspace of V. We saw last time that R3, or the set of all real vectors of length 3, was a vector space. So now let's look at a specific choice of vectors contained within R3 and see if it makes up its own vector space, thus qualifying as a subspace of R3. For this example, we will choose a set S made of vectors that have the form x, 0, negative x. By limiting the form of the vector like this, we have chosen a smaller set of R3, while knowing that our chosen set of vectors still follows the rules of the larger set. What we must check now is if our smaller set is closed by checking the two properties of closure. First, let's multiply a vector x by a scalar c. Distributing the scalar c, we end up with a vector cx, 0, negative cx. Notice that this still has the same form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S. Next, let's take two vectors, x and y, both from the set S, and add them together. Provided that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of the first, and once again, we find a result in the same form as we started. This means that the sum is also contained in our set S. We have verified that S is closed, making it a vector space, and because it was contained within the larger vector space V, this makes S a subspace of V. Before going further, it's important to introduce a few more concepts. Once again, let's say we have a vector space V and a number of elements of V, which we can call V1, V2, all the way to Vn. Any sum of these elements multiplied by some scalars, which we can represent as A1 V1 plus A2 V2 and so on, up to An Vn, is called a linear combination. The set of all possible linear combinations of these elements is called their span. As an example, let's take three vectors from R3, those being 2, 1, negative 1, 0, 2, 2, and negative 1, negative 1, negative 1. The span of these three vectors will be given by the linear combination AV1 plus BV2 plus CV3, where A, B, and C are all scalars. Let's plug in our vectors and distribute the scalars, and then do vector addition to see that the span of these three vectors has the form 2a minus c, a plus 2b minus c, negative a plus 2b minus c. It's worth noting that the span of any number of elements of a vector space V is also a subspace of V. In fact, it is the smallest subspace of V that contains that set of elements, as it is the intersection of all subspaces that contain them. Span will end up playing a significant role when it comes to completely describing vector spaces, but for now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.